The end result of all the decomposition that happens is heterotrophic respiration. And heterotrophic respiration is a large part of the carbon budget of ecosystems. It's not autotrophic respiration, driven by plants, but instead all of the organisms that are using plants for respiratory purposes. Heterotrophic respiration by soil microbes and animals is one of the largest avenues of carbon loss from ecosystems. And in most ecosystems, it's the largest loss of carbon. Now, often, ecosystem ecologists will measure soil respiration. And this can be measured in a couple of different ways. But essentially, it's an index of the respiration of microbes and of roots, as well as other organisms in the soil, but primarily microbes and primarily roots. Now, patterns of carbon loss from soils, soil respiration, tends to be driven by leaf area. The more leaf area you have, the more photosynthesis, the more leaf production that enters into the soil, as well as carbon allocation that is directly into the soil, that is then respired by roots or other microbes. So the more leaf area you have, the more carbon that gets fixed in one way or the other gets into the soil and eventually is respired. This graph shows the relationship between soil respiration and NPP. So on the x-axis, we have NPP. The units is grams of carbon per meter squared per year. And again, NPP is the amount of biomass that's produced in an ecosystem in a given amount of time, here, years. Soil respiration is on the y-axis. And again, it's grams of carbon per meter squared per year. The same units as NPP. So we can take a look at what's the relationship between how much carbon comes out of the soil as biomass is produced. And essentially what you see is that those ecosystems that have high NPP also have a lot of carbon being lost from the soils. So M here is a wet tropical forest, T is tundra, and you have ecosystems here in the middle. Those ecosystems with the highest productivity have the most amount of soil respiration. And again, soil respiration is going to be the combination of respiration from microbes plus respiration from roots. Now, the authors also point out that if you were to draw a one-to-one line here, and that's not easy to do, which would show equivalence in NPP and soil respiration, you can see that for a given amount of NPP, you actually have more respiration than you do NPP. And the reason for that is that soil respiration is not just due to decomposition of biomass, but also allocation of carbon to roots that isn't counted in NPP. They point out that there's a 25% difference or so, and they associate that with root respiration. It doesn't mean that 25% on average of the carbon that comes out of the soil is root respiration. It's probably a little bit higher than that, but there's more carbon that comes out of the soil than biomass is produced. Most important thing to remember here, high productivity ecosystems, high soil respiration, low productivity ecosystems, low soil respiration, both because there's less biomass to be decomposed and less carbon that's being allocated below ground. Now, this is a summary diagram to take a look at state factors and interactive controls, those proximal and distal controls on heterotrophic respiration for ecosystems. If we work our way backwards again, the size of these arrows has to do with the relative influence on heterotrophic respiration. So the direct controls are litter quantity, how much litter is produced, which then is available to be decomposed, and the quality of that litter. High quality litter, more respiration. In addition, litter C to N is important for determining heterotrophic respiration also. Oxygen, temperature, and water all have positive impacts on heterotrophic respiration. So these direct controls have to do with the quantity and quality of carbon, as well as those proximal factors that directly impact the ability of microbes to respire. Oxygen, having enough water, and also high temperatures will positively impact heterotrophic respiration. So those are the direct controls. And the indirect controls are primarily considered to be NPP. The more NPP you have, the more litter, and the more heterotrophic respiration. If we work our way backwards and think about how biota, time, parent material, and climate Climate has direct effects on heterotrophic respiration. So warmer, wetter climates are going to have more water, higher temperatures. So there's a direct end effect. But also climate determines soil resources. And it's the soil resources that determine NPP, as well as the quality of the carbon and C to N ratios, for example. So just like we saw with other ecosystem factors, the state factors and interact controls have both indirect and direct effects here on heterotrophic respiration, that is decomposition.